track down the defects, the material tester uses the pulse echo method. This is how a typical probe looks like. Under the bright wear plate, a piezoelectric disc is installed. It can transmit and receive ultrasonic pulses. A computer operates the probe via a plug-in card and power electronics. On the monitor, the intensity is plotted upwards and the time is plotted to the right. After placing the probe on top of the cylinder, initially no echo at all may be seen on the monitor. The reason for this is the too small contact area between the probe and the workpiece. Only with the use of a gel, the so-called couplant, the ultrasonic pulses can get into the workpiece and can also go back into the probe. Now the back wall echo turns up on the monitor. The material tester spreads out the gel evenly on the top surface. That way she is able to examine the entire cylinder. Using the velocity of sound in the material, one can plot the calculated depth on the monitor to the right instead of time. A very useful feature. With the help of so-called trigger gates, which may be set on the echoes with a computer mouse, the depth of the defects can easily be read off at the lower left-hand corner of the monitor. The cylinder back wall lies in a depth of about 200 millimeters below the probe, so the cylinder has a height of 200 millimeters. And here we go. The material tester scans the upper front end of the cylinder with a probe and observes the monitor. A defect echo appears on the monitor. This defect is located in a depth of 130 millimeters below the surface. Another echo indicates a defect in a depth of 87 millimeters. The second, smaller echo at 174 millimeters is caused by double reflection on the same imperfection. And these are the defects. A drill hole and a saw cut. Filled up near the surface and painted, they are not visible from the outside. The drill hole in a depth of 130 millimeters. The saw cut 87 millimeters below the surface. Trams are